In this video, we present our paper called Approximate Manifold Defense Against Multiple Adversarial Perturbations that appear in IJCNN 2020. In this paper, we present a new defense model called RBF-CNN that provides robustness for any LP greater than 1 perturbations without using adversarial training. Here, we propose to capture the density of smaller image patches instead of complete images to improve the scalability of manifold defenses for complex natural image datasets. In our experiments, we have shown that our proposed model can provide robustness against L1 or L2 or L infinity bounded perturbations. It can provide certified robustness against L2 bounded perturbations. Further, it can provide interpretable loss gradients. An adversarial attack attempts to fool a classification network by modifying an input image with minor perturbations. For example, we can calculate that perturbation in terms of L1 or L2 or L infinity norms. Existing defense models typically provide robustness for one particular type of perturbations. We can categorize them into three groups. Adversarial training can provide robustness for multiple perturbation types. However, it requires to generate adversarial images from all perturbation types. It increases the training time. Further, it raises an important question of how many perturbation types should we consider for our training. On the other hand, randomized smoothing can provide robustness only for L2 perturbations. Manifold-based defense models rely on the generative models to produce pseudo-clean images before classification. However, due to the limitation of the existing generative models such as GAN or VAE, their success is also limited for small datasets such as MNIST. Now we present our proposed defense framework called RBF-CNN that consists of an RBF layer and a reconstruction layer prior to the actual classification network. An RBF layer behaves like a convolution layer. Given an input image, we extract the patches. These patches are then applied to the filters of the RBF layer to obtain the feature maps of match scores. Our reconstruction process does not require any parameter. For an input image, the reconstruction process is as follows. For an input image patch, we get the match score from the RBF layer and we use them to construct the weight vector. Next, we sample patches from each RBF filter and then we reconstruct the image patch by using the weighted average of these samples. As you can see that the reconstruction process introduces randomization in our network. Hence, during the testing phase, we take an average of M predictions to obtain our final prediction. In our paper, we prove that the reconstruction process mitigates any minor LP greater than 1 adversarial perturbations. Here we provide two examples to empirically demonstrate this claim. We can see that the Euclidean distance between the clean image and the adversarial images are decreased irrespective of what adversarial attack we have used and what threat models we have used after we apply our reconstruction process. For our experiments, we have used two different RBF-CNN models called RCNN and RCNN+. We have experimented using MNIST and Cypher10 dataset. In this paper, we primarily compare our model with L infinity bounded adversarial trained models. Under L infinity attacks, we achieve similar performance as the adversarial trained models when the adversarial images are generated from the same boundary as used to train the adversarial trained models. However, as we increase the boundary, our model outperforms the adversarial trained models. We consistently outperform Madri's adversarial trained models under L1 and L2 bounded attacks. We have also shown that our model can provide certified robustness for L2 norm. We now compare the training time of our RBF-CNN models with the adversarial trained models. As you can see that our best RBF-CNN models can be trained at 4.8 and 7.2 times faster compared to the adversarial trained models. We have also demonstrated that our RBF-CNN models produces interpretable loss gradients with respect to the input pixels. This loss gradients represents the most important pixels of the image for the classifier. Previous studies have shown that such behavior cannot be observed for standard non-robust models. It can only be observed for robust models. Further, as we iteratively add these loss gradients with small steps to the original images, We observed that our RVF-CNN model generates new images with saliency features of different classes. In summary, we have proposed a new manifold-based defense model that achieve robustness for any adversarial LP greater than 1 perturbations. To the best of our knowledge, this is the first manifold-based defense model that is scalable for complex natural images. While we provide robustness for LP-bounded adversarial attacks, we do not provide any guarantee for other type of perturbations. Such perturbations can be measured in terms of color, rotation and translation, or other spatial transformations. It is important to note that it is still an open problem to build an universally robust defense model against any adversarial attacks. Thank you.